We are live. Rotate.
Hello friends, Namaste, all of you Namaste everybody and myself, S.S.Takalkar, आपको सुबह teacher. Dear friends, we are going to define very important terms today, its concepts and the problems based on all these definitions, all these terms. So this is a very important point here. The topic in this sorry for the interruption. Dear friends, we are going to verify the first law for the enthalpy also. If the energy is supplied to the system in the form of the heat energy and in the form of the work, then the internal energy of the system will be increased. So this is the first law of the thermodynamics, right? So here the internal energy of the system increases if the energy is supplied in the form of heat energy and the work to the system. So work done on the system, heat is absorbed by the system, its internal energy increases. Now, also you know last time we have derived W is equal to minus P delta E for both processes, compression as well as the expansion. So here one can substitute here, this can be then the minus P delta B delta U, or at constant pressure is considered, so one can write here, or this QP, this rearrangement, one can obtain delta U plus P delta E, right? So compare these two equations, this equation also here, this equation. So what is obtained here? Delta H is equal to delta U P delta E. Similarly, the QP is equal to delta U P delta E. Both are same. So here left hand sides are same, therefore right hand sides are also same. So QP is equal to delta H. We can write here the QP is equal to delta H, enthalpy change of the system because the reaction. The enthalpies of the processes are nothing but the amount of heat absorbed or evolved by the processes, right? So this is one of the derivation obtained from the first law of thermodynamics. Okay, now consider the one more concept which is very important and it is required today. The molar heat capacities, heat capacity, specific heat capacity. What is that? Heat capacity. One. Heat capacity denoted by C. It is already discussed during the last lecture, but in short, here the first consider specific heat. Specific heat. What is it by? Can be denoted sometimes as. Okay, so this can be by the definition. The definition: the amount of heat absorbed by the substance. That is 1 gram substance to raise the temperature by 1 degree Celsius. So here the S can be for 1 degree Celsius temperature and 1 gram substance. Okay. So amount of heat absorbed in Joule suppose. Then to raise the temperature by 1 degree Celsius, what over 1 gram substance. So one can here write yes, the specific heat of that substance is nothing but the delta T. What is the temperature difference and the 1 gram, so whatever is the mass. Okay, so here again specific heat is equal to, one can write here, it may be in joules, and here the mass in grams and temperature difference, whatever we make, this is in grams and this is in degrees Celsius. Okay. Now, if the process carried out at constant pressure and or constant value, then the specific heat or heat capacity can be further written as the heat capacity at the constant pressure. Molar heat capacity at constant pressure or molar heat capacity at the constant value. Okay. Let us consider this one. So for the definition, the molar heat capacity, that is the amount of heat absorbed per mole of the substance to raise the temperature by 1 degree Celsius. Right? So this is in joules. This is the number of moles. Yeah, these are the moles. And this is the temperature difference. Right? Temperature difference in that. So here the amount of heat absorbed by 1 mole of substance to raise the temperature by 1 degree Celsius, right? That is called as a molar heat capacity. If it is carried out at constant pressure, can be written as, and it is considered the mole, so sometimes written as also the mole also. Yeah. Okay. Or simply this can be also written as the molar heat capacity Q for N delta T. Right? Or sometimes, so one can write here this formula also. C is equal to Q for N number of moles delta T. Okay. So here this is about the heat capacities if the process carried out at constant pressure. Right? So if the constant pressure is there, QP, it can write here QP, or CV is equal to QV if the heat absorbed at constant value, right? Amount of heat absorbed at the constant value or 1 mole of the substance to raise the temperature by 1 degree Celsius. Right? So whatever temperature increase, so divided, we converted it ultimately into the per degree Celsius per mole. Okay. Now consider the today's point, enthalpies of different processes. So continue. The enthalpies of different processes. What are these processes? We are going to study the different processes. And the enthalpy change, that means total heat change during the processes. It may be a physical changes, physical processes. It may be a chemical processes. Whatever it may be, we are going to study one by one. So here, in fact, instead of the absolute value, yet which is actually cannot be determined, the enthalpy change is always determined. So we can write here the enthalpy of the different processes, that means it is nothing but the delta H, that is the enthalpy change. Sometimes the enthalpy of the product decreases, sometimes enthalpy of the product increases in the reactors, and depending upon it, delta H may be a positive or negative. Right? So here the enthalpy change for different processes. One, physical change. Right? So this is the some processes we are going to study some physical changes. Second, chemical changes. Generally, the chemical reactions are considered, and also delta H can be calculated by using the bond energy or bond enthalpies. Because you know, when any chemical reaction is taking place, old bonds are break, new bonds are formed. So here the concept is based on the bond energy, right? So what is the bond energy? So here the amount of energy required to break a bond, right? And it is again considered that the same amount of the energy also stored in that bond. Right? So here the amount of energy required to break a bond is equal to, right, the energy required to break of bond is equal to the same energy, that is the energy stored, energy stored in that bond, when it is formed, when it formed. And therefore the enthalpy of the reaction, enthalpy is that which enthalpy change when that process taking place, when that chemical reaction taking place. So it can be determined on the basis of this one. And in short, I am going to write here the total enthalpy changes of the reactants minus sum of the enthalpy changes of the products. Remember, this is a very significant formula. All other cases, the products minus reactant is there, but here the reactant minus product is there. So details about the calculation of delta H, or a given reaction using the bond energies, we are going to study for exothermic reaction and for endothermic reactions afterward. But you consider the delta S, that is the enthalpy change of the reactions, can be determined using the bond energies, and it is based on that the energy required to break the bonds, that particular bond, is always equal to the energy that is stored in that bond when it is formed. Okay. Now we are going to study today the physical changes, the different physical changes, and how the enthalpy changes is calculated. Enthalpy of changes, or the heat of that changes, total heat, right? Delta H. Okay. Now study one by one. Here. Dear friend, as you know, the physical changes, for example, the one phase change, that is solid to liquid, liquid to gas, or direct solid to gas sublimation processes. Secondly, sometimes the atom or molecular changes also taking place in one here. So what are the physical changes? So if you consider a very known example of the H2O, when it is a solid, that is nothing but ice, and then it can be heated, absorption of heat, then it can be converted to liquid. Again H2O, then further heated into the gas. So here at 0 degree Celsius, what happens? There is an equilibrium between the solid state and the liquid state for the water, and the temperature is found to be T is equal to 0 degree Celsius and P is equal to 1 atm pressure. So this is nothing but the fusion process, melting process. The ice melt at 0 degree Celsius and 1 atm pressure. So this is the melting point. So what is the melting point? Where the vapor process of the solid and liquid becomes 1 at 1 atm pressure. Right. So here the fusion process taking place from left to right, and the amount of heat absorbed during this constant pressure is constant. Suppose there is a 1 kilogram of ice, and if you heat, the temperature should not increase until all the ice melted into the water. So there is a equilibrium. So where does this heat, given heat is goes? That is hidden into the water, right? So it is a latent heat of fusion, hidden latent heat of fusion. So here that is also known as the enthalpy change for fusion F, right? And it is found to be 6.01 kilojoules per mole. Consider this. So plus 6, that means this amount of heat is absorbed at equilibrium, at constant temperature and constant pressure for 1 mole per mole, right? Per mole. So here this can be defined as latent heat of fusion, can be defined as the amount of heat absorbed by 1 mole of solid substance and constant pressure and temperature. This is a very important word because pressure and temperature must be constant. It is not increases until all the solid is melted at the melting point as well as during the vaporization, that is the boiling point. Temperature cannot be changed, and if we consider this is the boiling process and the temperature here is 100 degrees Celsius, this is opposed to 1 atmosphere pressure. So this is the boiling point. At this boiling point the water boil. So what is the definition of boiling point? That is the vapor pressure becomes 1 atm, right? Vapor pressure of this, they are in equilibrium. So one can represent like this also. So at 100 degrees Celsius constant pressure, all the water, given water, all the quantities converted into the gas, temperature remains constant and at 1 atm pressure, right? So here the pressure of both the vapor pressure of the liquid becomes a 1 atmospheric pressure at 100 degrees Celsius, and because heat is absorbed. Suppose this is the water and we are going to, there is a thermometer, the temperature is always constant until all the vapor going to vaporize. So where does this heat is utilized? This heat is stored in the form of gaseous state of water. So latent heat of water, and it is also the enthalpy change of vaporization, that is vaporization enthalpy change, and it is found to be the for this water is 40.7 kilojoules per mole. So how we define the enthalpy change of the vaporization? So here the amount of heat absorbed per mole of the substance or enthalpy change accompanying the vaporization process for 1 mole of substance and constant temperature and constant pressure. So this is very important here and here also both cases. Okay. Right. Also, if you consider the sometimes this is directly taking place, solid to liquid here. So this is the sublimation process, right? Solid to direct gaseous state, sublimation process. Okay. So here the enthalpy change that is accompanying per mole n is equal to 1 mole of the substance at the constant temperature and pressure are constant. Okay. So in this definitions, that is the whatever it may be, enthalpy change of the pressure, enthalpy change in the vaporization, or enthalpy change in the sublimation, or here also the opposite thing. The gas can be converted, that is the heat of condensation, right? Or here the liquid can be converted into the solid, so it is a freezing. So here it is minus 6.01 kilojoules per mole, and here it is nothing but minus 40.70 kilojoules per mole. So the enthalpy change of the condensation process can be defined as the enthalpy change when 1 mole of the gaseous state of the substance is converted into the liquid state at constant pressure and temperature. This is very important. Or the enthalpy change for the this process, freezing process, right? When 1 mole of the substance, liquid substance, is converted into the solid substance at constant pressure and constant temperature, that is the enthalpy change or enthalpy of the freezing, enthalpy of the condensation, enthalpy of the vaporization, enthalpy of the fusion. So for 1 mole of the substance is considered for the particular change, 1 mole of the substance, and temperature and pressure must be constant every time. Okay. Now Sometimes the gaseous substances can be converted into the solid. So it is this type of process. So this is a lattice formation. So the H lattice formation. Okay. Now in this case the sublimation, that is solid, one mole of the solid at constant temperature and pressure, it is converted into the gaseous state of the substance. The enthalpy change is called as the heat of sublimation. Okay, so one can determine it as delta sublimation. It is found to be the 51.08 kilojoules per mole. It means 1 mole of substance, 1 mole of ice, right, is converted by absorbing this much amount of this kilojoules of the heat, right, at constant pressure and constant temperature. It is the heat of sublimation. So actually, what is it? Here the plus 6.01. So here it is the at constant temperature and pressure the conversion is taking place. Here also conversion is taking place. So here from 0 degree Celsius, liquid water at 0 degree Celsius, right, to 100 degree Celsius, the enthalpy, the heat is absorbed by the water, right, and it is calculated by the formula, that is the Q is equal to the, for the moles, what is the moles? For suppose 1 moles, right? Yeah. Into the heat capacity of the water, for the liquid water, heat capacity for the liquid water, right? Heat capacity at constant pressure and temperature change. So this is nothing but 100 degrees Celsius. This change, right? Heat capacity of given water and this for the 1 mole. So by using the value of heat capacity for the liquid water, that is the amount of heat absorbed by the substance to raise the 1 degree Celsius temperature by 1 gram, or for 1 mole is considered heat capacity. So one can calculate. So here this is very useful term, that is the heat is absorbed by the water, right, from convert or goes to the 100 degrees Celsius, from 0 to 100 degrees Celsius, right. So heat is absorbed and it is calculated by this one. So amount, how many moles are there? Is there heat capacity of liquid water and temperature difference, that is from 0 to 100 degrees Celsius, right. Whatever is the temperature difference. Okay. Now let us consider the opposite process, the sublimation. Latent heat, here the enthalpy latent heat of that processes, latent or lattice, sorry. Here the lattice is for, that is if there is a gaseous state of the ions, positive ions, negative ions in a gaseous state, then they come and forms a solid. So in this case the amount of heat liberated when 1 mole of gaseous substance, generally the ionic substances from the lattice. Okay, the 1 mole of the ions in their gaseous state, right? Gaseous state is important. Gaseous ions, 1 mole gaseous ions are converted into their solid state, crystal state. Okay. So here the enthalpy change accompany when 1 mole of the gaseous ions, right, they forms a crystal state, that is a solid state, right. So here that enthalpy change is nothing but the lattice enthalpy. Okay, we are going to study in during solving the problems also this one. Now consider. So this is yet to consider the different definitions. Enthalpy change is one, that is fusion or vaporization, heat of vaporization, similarly heat of sublimation, and is the condensation, freezing, and lactation. Okay. So in this all these cases here, the 1 mole of the substance is considered, and temperature, pressure must be constant at constant temperature and pressure. Then 1 mole of the substance is going to under the process, whatever is the change, solid to liquid, or liquid to gas, or solid to gas, etc. or opposite. Now, secondly, we are going to study second type, that is ion or molecular changes. Molecular changes. For example, consider the example. Suppose calcium giving calcium ions. Again, this calcium ion giving calcium dipositive ion. So here it is found that this must be in gaseous state. Consider again, very important. Not a solid state. For the solid calcium is converted into the calcium liquid, into the calcium gas, and this calcium gas, then this ionization taking place, right? Okay. Now directly calcium solid to calcium gaseous state, because some extra energy required to obtain the calcium solid into the liquid, liquid to gaseous state, and gaseous state, then it is considered. The first point we are going to study is heat of ionization. What is heat of ionization? So here, first thing, 1 mole of gaseous atom or ion is considered. Here it is atom, here it is ion. So whatever it may be an atom or ion, it must be in a gaseous state and gaseous 1 mole, right? So then whatever is the enthalpy change accompanying this change, formation of its ion is converted into ions. Okay, right? So if you consider this example, the enthalpy change of this is found to be 450 kilojoules per mole. For this, right? And for this, it is 1150 kilojoules per mole. What it indicates? MOL or MOL? What do you mean? Potassium. So here, to form univalent calcium, monopositive ions of the calcium, this amount of heat is absorbed. Plus is there, plus, right? Plus. So this is the enthalpy of ionization. This is the first enthalpy of the calcium. Second enthalpy of the ionization, second ionization enthalpy, right, is 1150 kilojoules. So there is much difference. What it means? It means to remove the 1 more electron from the calcium ion is more and more heat is required, because this is there is a more attraction between the electrons and the nuclear positively charged nucleus of the calcium ion, right? That means net charge, right, on nuclear charge, of course. Net nuclear charge on the outer electron is increased, right? So more energy required to remove the second electron from the calcium ions, and therefore 1150 kilojoules, this much amount of heat is required. So what is the definition now? Consider 1 mole is considered first thing. Secondly, gaseous state of the atom, right? Gaseous state atom or ion, 1 mole of gaseous state atom or ion, right? Amount enthalpy change accompanying when 1 mole of the gaseous state atom or ion converted into ion. It's ions. Okay. Now consider the one more example also. Suppose the chlorine, Cl. It is actually a gas, right? Cl is a gas. Then Cl plus C. What is it? Undergoes dissociation, right? Or formation of atoms, right? This molecule dissociates or formation of atoms. So this is nothing but the heat of the dissociation or heat of the atomization. So formation of atom from its molecule. So all the molecules from 1 mole of the substance, right? 1 mole of substance in its gaseous state, dissociates to give the atoms, right? Gives the atoms or radicals, whatever. So here 1 mole of the substance in its gaseous state dissociates. So whatever is the enthalpy change, that is called as the enthalpy of dissociation or enthalpy of atomization. Okay. Now it is found to be this chlorine is found to be delta atomization H is equal to kilojoules per mole. That means this much amount of the heat is absorbed by 1 mole of gaseous molecules of the chlorine. Whatever are the molecules in a 1 mole, all the molecules, they are dissociates. All the molecules in 1 mole of the substance in a gaseous state, they dissociate to form their atoms, right? So here again 1 mole and gaseous state. There is no question of the constant pressure and temperature like phase transformation. Okay. Now this is the definition. We define it. The enthalpy change when all the molecules, right? Enthalpy change accompanied when all the molecules in 1 mole of the gaseous substance, is dissociated in atoms. Okay. Now again, this Cl, suppose consider one of the Cl and electrons forming Cl minus. This is the gaseous. This is also gaseous. Electron gain forming the negative ions. Here is also formation of ion, but because of electron gain, and therefore this is the enthalpy change accompanying when electron 1 mole of the gaseous state atom or ion. It may be atom or ion. This is the atom, but sometimes suppose this is the oxide. Again oxygen. Divalent oxygen, univalent. Now it may be atom or it may be ion, right? 1 mole in its gaseous state, right, is converted into the ions, negative ions, by gain of the electrons. So here the enthalpy change during the 1 mole of gaseous atom or gaseous ion gains the electron and to form the negatively charged ions. Okay. So for this the chlorine electron gain is found to be the electron gain written like this is equal to. Now in this case the enthalpy change is the word is common word. Actually in this case in the dissociation processes the heat is absorbed, where in this case the heat is evolved, right? It is exothermic. This is the endothermic, right? So whatever is the thing, but one can define by using the enthalpy change. It may be a heat absorbed or evolved. Okay. Then for the electron gain, the enthalpy change for this chloride ion formation is found to be 498 kilojoules 1 more. And as energy is evolved here, the negative sign is here. Yeah. Oh. Here, consider these values against here and you will write the enthalpy change during the electron gate Eg is equal to minus because it is all that is minus sign. You are for this reaction and it is 348 kilojoules per mole. Okay. So here we have studied in this case the enthalpy of atomization or also known as enthalpy of dissociation. Similarly, electron gate. Similarly, ionization. In all these cases, always 1 mole of the substance is considered in gaseous state. Right? So, whatever are the processes depending upon it, 1 mole of the substance in its gaseous state is converted into its ions or in atoms. Right? Dear friends, we are going to stop today here, and in the next lecture I will explain the remaining part, that is the enthalpy change accompanying the chemical reaction and how the enthalpy change is calculated or determined using the bond energies or bond enthalpies.